Greetings and welcome to a new video about multiple feedback circuits. This is our example where we discuss the low-pass filter design. Of course, we will see everything step by step in our calculations and verify these in SPI simulations. Now, before we jump to our design example, let's first briefly discuss what is a multiple feedback low-pass filter. The circuit is shown here. You see here two negative feedbacks. This is the first through the capacitor C2. Another one, the second one, through the resistor R3. So that's why it's called the multiple feedback configuration. The first low-pass filter is shown here, which is then this R1 and a C1. The other one is created from this R2 and a C2. And R3 here is also used for the gain setting. We will see the details shortly. First, we will start with the transfer function of this circuit, which is the output voltage divided by the input voltage, which is shown here. You see here the expression. It has a negative here, which is then an inversion because this is an inverting operational amplifier circuit. You see also the second order expression in the denominator, so we have also a second order filter. Now this is also the transfer function you will use in order to calculate the resistors and the capacitors in this circuit. Now we can make the simplification or the calculations more easily by using the exact same capacitors for C1 and C2, so we can also define it as C. This will reduce also the number of unknowns in our design, so it will also speed up the process. Now then we have this expression you see here. Now the C1 and C2 will be then C, so you get a C squared. This will be just a C here, and you get also a C squared here, so you see it's more easily written in this form. The standard form of a second order low-pass filter is given by this expression. You see here the K, the omega n, and also the Q, and those are the following. We have the K, which is our passband gain. Now for a low-pass filter, that means actually the DC gain. The Q is called the quality factor. It defines or creates a specific shape. So in order to make the shape sharper, you can go for a higher quality factor. The omega n is our natural frequency. Now the comparing terms with our transfer function here from this circuit and the transfer function from a standard second order low pass filter, we see the following. We see here that this term here, which is exact same here, is omega n squared. You also see here the numerator, which is in the top part of the transfer function, is k times the omega n squared, including that minus sign. You also see here this part completely in front of this parameter s, which is our Laplace parameter. That is then equal to omega n over the q. So we have three equations and also the parameters for this standard form, but we have more unknowns. So that means in the final design we need to select some components in order to calculate the other components. So from here we can now set up the design equations in order to calculate the components from a specific design example. The omega n here can be calculated by taking the square root of this one that is actually shown here. And if you use, of course, the exact same capacitors, you can also have this as a square root of the product of this R2 and R3 and the square root of the C square root, which is C. You see that also outside this square root. The K will be then, by making use of these two equations, will result in the minus R3 over R1. And as I said in the beginning, the R3 is really here to set the gain, including of course this R1 here. So the gain can be then set by the ratio of these two resistors. And this is, by the way, also called the DC gain. The quality factor is calculated using this formula. This is really the work out of the omega n squared here, of course taking the square root. And working out, so a couple of steps, you will end up here. Again, here you can use the capacitor. C1 and C2 is equal to each other. Then you get here the square root of C1 will be divided by the square root of C2, which is the exact same. So that will then result in this. So you have no controller or no action of the C in the quality factor. Okay, now we will use several formulas, like the formula for the bandwidth or the cutoff frequency in this low-pass filter, and also the resonant frequency. Those are all related to the omega n, which is our natural frequency, and also the quality factor. I leave the details out how this is derived. This is of course some work, but this is what we can use. Which you also see is interesting because most people, or also in the literature, some books also, say that the resonance frequency is equal to the natural frequency, which is of course not true, because you see here the quality factor is then also comes into play here, so we will have some other definition. There is also the MR here, which is then the gain peak-in value, which is also related to that Q, which is our quality factor. So again, in summary, omega bandwidth is the radians per second in this formula. You have here this omega R, which is our resonance frequency, which is the actual resonance frequency, not the natural frequency. And we have also this gain peak-in at that resonance frequency. We will see this in more detail when we do the design example. Okay, these are very important components and values we will need to use in our design. By the way, this is only valid if our Q is equal to or larger than the 1 over the square root of 2 or the square root of half. So if you have a Q, let's say 0.1, this is not valid. You can see that also from this expression. In order to have this expression valid, you need to have the Q which is equal to or larger than 1 over the square root of 2. Okay. Let's now go in more detail what the quality factor does. In general, we have a plot like so. That can be, of course, the case where you have a quality factor which is high. And then this is, by the way, for the low pass filter. You have again our DC gain, and it gets some peaking at that resonance frequency, and then gets a slope here, and then we get a slope of minus 40 dB per decade. And this distance from this low frequency and this peaking part, that's what we call the MR, which is our gain peaking. So here we have the total gain, and this is, by the way, in the scalar form. So in order to convert that to dBs, which is this scaling, you need to do the 20 log of that MR. But this is what you calculate here. That will just be the scalar value. The resonance frequency, again, that is again calculated using the natural frequency and the quality factor. Now some values for the quality factor and the gain peaking, and also this in the dBs. You see here the 0.7071. This is the approximate value of this 1 over the square root of 2. Then the gain peaking will be exactly 1. So from this formula, that will be, of course, 0 dB. Now if you increase your quality factor to 1, to 1.5, you will see different values for your gain peaking. So the gain peaking will also increase. So in this case, you see the gain peaking is almost 7.5 here, or maybe 7, depending on, of course, the accuracy of your reading. That might be, for example, between the 2 and the 3 here. Okay. Again, this is only valid for Q is equal to or larger than 1 over the square root of 2. Okay. Let's see more details by looking at the plot where you see several values of the quality factor. Again, the quality factor which is at the edge, which is our 0.7071, or more exact 1 over the square root of 2. You see also here the quality factor Q is 1, 1.5 and 2. Now this is again valid for this situation. When you look at now the peak value here, which is at resonance, this is now also normalized for the natural frequency. So in this case, you see that this is happening here, and the gain here in the scalar form is 2.0656. And that is for Q2, which is also shown here. Now for the other one, which is then at 1.5, again the gain peaking value will be there, 1.5910, which is also what we see from the table. The other one with this black line here, which is for Q is 1, for quality factor 1, it will be then 1.1547. Okay, let's now go to our design objective and use this circuit. Now we will use the circuit here and have the specifications as follow. We need to have a cutoff frequency which is exactly 1 kHz. The passband gain should be -10 because it is inverting. That means actually in absolute sense 20 dB. If you convert that using the 20 log of the absolute value of this one. And our gain peaking is to be 4 dB. In this case I have used MR as 4 dB, but it means of course MR in the dB units. Then we also need to calculate our resonant frequency. That means at this frequency we get this much gain peaking in dBs. Okay, let's do our solutions. First we start with the passband gain, because that is what we need here have as -10. And that is the formula we need to use here, which is then minus R3 over R1, and that must be then -10. See here two unknowns, so we can now select one of the components, let's say R1 or R3, and we calculate the other one. I will now select R1 as 1 kilo ohm, and then we can calculate R3 as 10 kilo ohm. So that will be then a ratio of 10 here. So that is done. So we have now the R1 and R3. Now the gain peaking of MR was 4 dB. We can convert that to a scalar value using the formula as 10 to the power 4 over 20, which is 1.5849. And then we can use the formula, which is then in the scalar form, as 2q squared over 4q squared minus 1 in the square root. And we know this, which is then this, 1.5849. And we need to solve this in order to calculate the q. Now, we can do that by using the solver. So you can use that in the calculator. That will result in a quality factor of 1.4934. So it's approximately 1.5 as the quality factor. Now, using the quality factor, we can now move on and calculate other component values in this circuit. Now, the quality factor we have for this circuit was this formula. You see here again the resistors, the capacitors in this formula. Now, in this case, I will select R2 to be 400. Before I select that, let me first make the reason why I do this, because we know the resistor R3 and R1. But we also need to know the C1 and C2 and also R2. So we have here 3 unknowns. And we have only one equation. So it needs to be also, we need to select again some component values. So if I select 400, for example, then we have here 1.4934. That will be then equal to that one. You see here this 1000. So 1 kilo ohm. 400 times 10,000, which is our 10 kilo ohm for R3, times the C1, which is still unknown. And the product of these 3 resistors here in this format, and then you get here values, and again the square root of C2, which is still unknown. And what you see here is everything is known here except the capacitor C1 and C2, but they are of course here also in the square root. So what we can do, we can also write this like so. This is 400 times 10 to the power 4, that means 4 times 10 to the power 6. So you get it out, that is actually the square root of 2 million. 4 million, so you get actually here 2000 out. So 2000 times 1000 will be then 2 million. And again, square root of C1. Now, divided by this part, which is actually this part, so 14.4 times 10 to the power 6. You see already some expression which is more convenient and also easy to see. Because this is now equal to 2 million over this 14.4 times 10 to the power 6, which is actually 14.4 million. Which is just 2 over this 14.4, which is exactly 5 over 36, times, of course, the square root of the C1 over C2. Now, we need to calculate this, and of course, we can calculate the ratio of the C1 and C2 here. So first, we do 1.4934 divided by this one, and square the result. That's actually what you see here, which is then 115.62. Or you can say C1 is this much times C2. Okay. We will use this formula later. So this is now a ratio between the C1 and C2, of course by choosing the resistors like so. Okay, now the cutoff frequency, we have already given that in the slide presentation before. We have here now the bandwidth, which is our natural frequency times this expression where you see all the Q's in these square roots. Now we know the Q, because we just calculated that here. We also need to know our omega n, but we know from our specification that our bandwidth must be 1 kilohertz. This is, by the way, in radians per second, so we need to do 2 pi times this f bandwidth. So you see here 2 pi times 1000, which is then this one. What you see is, indeed, we need to calculate the omega n. That can be done by using 2000 pi, which is this left side, divided by this complete thing here. Now this is just a number, so you can just type this in your calculator. And that will result in the omega n, which is then 4398 radians per second. Now this is the natural frequency. Now we know also the natural frequency formula, which is then given by this expression, 1 over the square root of the product of the R2, R3, C1 and C2. In here we actually have all the component value except the capacitors here. But we know that the capacitor ratio of the C1 and C2 is also this. So we can substitute here the R2, R3, and we can also say that C1 is 115.62 times C2, and then we leave the C2 as it is. So what I mean is actually the following. So use this value from omega n we just determined, So 1 over the square root of 400 times 10,000 times, again this, which is then from here, which is then replacing the C1 by this expression, times C2. Where you see, now you see actually that the equation have only one unknown, which is the C2. Now we can calculate that, that's pretty easy. So we actually take it here, so 1 over that one, and then square it to the left, right hand side, and then divide by this. It's actually all shown here. And then you have your expression as shown here. So it's actually now getting this 10.57 nanofarads. Okay, now we have our C2. We can move on and calculate the C1 using this formula. Now substitute here this 10.57 nanofarad will result in 1.222 microfarad. So we also have the C1. Now we have all 5 components in our circuit. The final one is the calculation of the resonance frequency for our final part here, which is then given by this formula. We need to have the natural frequency, we also need to have the quality factor. Now, we can do that by substituting the values, the quality factor here, and the natural frequency, and that will result in 3,874 radians per second, which is indeed not exactly as this one. Definitely not in this case. Okay, now let's go to the simulation circuit. The design is completed. We see here the R3, 10 kilo and 1 kilo we have actually selected here. R2 also 400 ohms selected, and you see here the C2 and the C1 we just calculated. Okay, let's now also look at the simulation result, which is our Bode plot. You see here indeed that the Bode plot is showing the similar shape as we have discussed. DC gain is indeed 20 dB as we wanted, because that's the 20 dB from the specification, passband gain or the DC gain. We see that the cutoff frequency is indeed 1 kHz. You see the gain is at DC 20 dB, so in order to get the cutoff frequency we need to go down by 3.01, so that's indeed 16.99 dB. And the gain peaking here happens at the 616.6 Hz, which is indeed here from 220 dB going up to 24 dB, which is exactly the 4 dB gain peaking we have in our specifications. But how do we prove that this resonant frequency is indeed correct? Now we know that we have calculated our resonant frequency in radians per second. That was this value. And when you divide that by 2 pi, you get now here 616.6 Hz, which is indeed as we have it here. So we have indeed as we have it simulated. That was our example concerning the multiple feedback active low pass filter. You have used the second order variation of this and used the transfer function to calculate the component values and verified our result using the SPICE simulations. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.